Okay, in the previous example, we went over the negation of a proposition, and that only involved one proposition, P, and then you negate P. Now we're going to talk about how we can have new propositions that are created from two or more existing propositions, and we can create these new propositions by adding in connectives. So first we're going to talk about the conjunction. Let P and Q be propositions. The conjunction of P and Q is denoted like this. P, and then we have a little upside down V and Q. Now this little upside down V is the symbol that stands for and that is the connective that creates the conjunction. So previously we had two separate propositions, P and Q, and then we created a new proposition by combining them with an and statement. In order for P and Q to be true, both P proposition and the Q proposition separately needs to be true in order for the new proposition, P and Q, this whole thing to be true. So let's look at the truth table of this so that we can put this together. Here's my truth table. So this is for the conjunction P and Q. So if I have P, I have Q, and then I want to look at my new proposition P and Q. Now, since I have two propositions here, I should have 4 rows. There's the first row, the second row, the third row, and the fourth row. And the reason why I know that I should have 4 rows is because I need to make sure I put in the truth value, all the possible truth values for P and Q. I have a spot for P and I have a spot for Q. And I want to find all the possible combinations I could have. I have 2 possible choices for P, which would be true or false. And I have 2 possible combinations for Q, which would be true or false. And when I multiply them together, I get 4. So that means I'm going to have 4 rows. There are 4 different combinations of true and false that I could have for P and Q. So I could have true, true. I could have true, false. Or I could switch it the other way and have P be false and Q be true. Or they could both be false. So these are all the different possible combinations. If I had a third proposition in there, or just so a little side note, if I had P, Q, and R, then I would have 2 possibilities for P, 2 possibilities for Q, and 2 possibilities for R. They could all be true or false, and when I multiply them together, I should have 8 possibilities of combinations of true and false. Just remember, when you're making sure that you have the correct number of rows, you use your counting principle. Okay, so now with P and Q, remember, in order for our new proposition, where this whole thing is stated together, in order for that to be true, I need both P and Q separately to be true. In this case, in the first row, I have P is true and Q is true. So that means P and Q is true. But if you notice, in all the other options, if I look row by row, there's at least one false in there. right? The second row has a false, the third row has a false, and in the fourth row, both P and Q are false. So that means for the second row, if P is true and Q is false, P and Q has to be false because they both have to be true individually for that conjunction to be true. So the rest of these are all false. And this is what our truth table looks like for a conjunction. Here's an example. We want to find the conjunction of the propositions P and Q, where P is her PC has more than 16 gigabytes free, and Q is the proposition her PC runs faster than 1 gigahertz. The conjunction of the two propositions means it's an and statement, and in order for the whole thing to be true, each individual proposition needs to be true. So if I want to find the proposition of this in words, here it is in symbols, P and Q. But if I want to find that in words, I would say her PC has more than 16 gigabytes free, and her PC runs faster than 1 gigahertz.